certain class of problems. Purely, not all problems, all image presence problems is the best tool. But for certain problems, where depth information is required, this particular tool really works out. So my outline of my talk may be organized like this. I'll give a very brief introduction to the topic and followed by defining the two different kinds of morphological operators, the binary morphological operator and rational morphological operator, and from that we will move to perfect transformation. This is not usual frequency domain or the orthogonal transformation. These are transformation, spatial transformation you find on the morphological operators only. And then I'll go for the little bit of mystical morphology and morphological transformation, which will give how an image, rational image, can be decomposed into some basic information and some detail or age information. And from there, we'll try to explore some of the applications where this kind of tools can be very useful. This will be followed by a soft morphology or define. Okay. Now, before I'm going to define formally, I'm just going to give a simple example. We all know what is the binary image. That's a two-level image, right? But in that two-level image, okay. Just. This is the original analog image. When we digitize it, basically think of dividing the whole image into very small blocks, and each block is given either on 0 or 1 depending on the black portion is covered by 50% or not. Right? So now this becomes a two-dimensional array of numbers. One we can describe with a two-dimensional signal, the x and y, and its value is the function. So usually the conventional approach to image processing gives an image as a two-dimensional signal. Right? Exactly similar with that is a graphical image, and a small block can be expanded this way, and each of the pixel or the small block can, depending on the intensity values, can be mapped between 0 and 250. So it's again a two-dimensional function as a multiple value. But in morphology, what we say that will not consider this image as a two-dimensional function. We'll consider the image as a set of points where the points are only the black points here. I'm interested. So my set, just in the set vector operator, they say consider only those points, those pixel values. And then this point will consider my set. That's like it. Similarly, here is a two-dimensional image can be converted to a three-dimensional surface, and that can be think of a three-dimensional point set in the three-dimensional space. So, in brief, if I summarize, is a conventional universal text speech with a two-dimensional signal, and we apply some linear operator or some orthogonal transform or convolution operator to get the result. And for image analysis or object recognition, we expect some features. This could be statistical features or structural features, and based on the statistical or structural features, we define the describe the image, and there is some model, and we compare this my extracted features as a model, and finally some of the results. But there are some limitations. If I deal an image just like a two-dimensional signal and move like it, the first thing, the image is not just a signal. When it contains or when you interpret an image, when you interpret an image content, I'll give just one signal as an example. It's not really just the signal value is sufficient to interpret it. We apply our knowledge, our experience, and also the context, completely can interpret a particular image. So, when you interpret an image, the process is neither fully objective nor fully subjective. So, in which version technology would you use some signal printing operator or the space domain operator? There is an absolutely quantitative in nature. There is a mathematical way defined. It may not always give the result. Okay. So we can just look at this simple example. This here. The first example, we have a set of state lines drawn in different orientations. But if we look at this image, immediately you can see a white effect. Right? But from the signal person's point of view, we really look at the signal that each and every point really no distinction. It comes because of an interpretation, our illusory interpretation, perception of the object of the image. You can look at that particular thing. Second, in the next example, there are two horizontal straight lines, and the upper straight lines actually are longer than the lower one. Just in contrary, if you just go by the signal person's point of view, just count the number of pixels, both the lines horizontal part has the exactly same number. Why the upper ones are looked after is longer? Because of the delimiter. Since the delimiter is not the vertical or the perpendicular one, it's the divergent, it appears somehow as if it is stretching the length of the line. On the other hand, the lower one squeezes the line. So because of this simple one case, our interpretation about that line is one is appears longer than the other. So in mathematical morphology, you will say you will treat that image as a set of several sets of points, and because we treat that image as a set of points, we can directly deal with the object set. So I'll give some examples how do we do that. And third, that's the most important thing. Morphological operator has two distinct parts. One is the absolutely quantitative, how do we define the operator. That's an absolutely mathematical sense. The second part which is absolutely subjective. It needs the definition needs a particular thing called the structuring